More than 10 years ago, I was teaching an advanced avalanche course. As part of the morning hazard evaluation, one group of participants rated the solar radiation for the day as intense. Another group of participants rated it as negligible. I was struck that experience-based estimates of solar radiation could be so different, especially since solar radiation is a quantity that can be estimated. Years later, I asked graduate student Laura Bakermans to develop a practical model for near-surface snowpack warming, which is closely related to solar radiation. She developed SWARM, a free spreadsheet that estimates near-surface snowpack warming over idealized terrain. Sometimes, daytime warming is not important to avalanche forecasting, but some of the conditions in which daytime warming is important to avalanche forecasting include 1. The first substantial warming of fresh, dry snow. A cohesive slab can form quickly. 2. A weak layer in the top 50 centimeters and near-surface snowpack temperatures headed to -5 degrees Celsius or warmer. 3. The first surface melting of fresh, dry snow. But before we get to SWARM, let's look at some of the processes that can warm the upper snowpack. First, solar radiation from the sun is absorbed by clouds and certain atmospheric gases, especially water vapor. These components of the atmosphere can radiate long-wave radiation. The downward part of that long-wave radiation can warm the upper snow surface, but the snow surface also efficiently radiates long-wave radiation, so the net warming of the snow surface by long-wave radiation is quite small. Warm winds, such as a Chinook or Foehn wind, can efficiently warm and even melt the snow surface, but it is difficult to estimate the local effect of these winds over terrain, so SWARM ignores this sometimes important factor. That leaves the shortwave radiation that passes through the clouds and the atmospheric gases. Numerous studies, including Laura's, have shown that the absorbed shortwave radiation is the dominant factor in warming the upper snowpack. How much reaches the snow surface depends strongly on the cloud cover. The amount that is absorbed, about 10% for fresh snow, can be estimated from the age of the snow surface. Here is a photo of my car window, which shows two of the effects that typically dominate the surface energy balance. First, during the night, it was a clear night, the long-wave radiation has cooled the window and frost has formed. In the morning, direct solar radiation has reflected off the mirror onto the window and melted the frost. It is this shortwave radiation that often dominates the daytime warming of the upper snowpack. Here is a temperature profile of the snowpack. During the night, temperatures cool mostly by outgoing long-wave radiation. During the day, temperatures warm mostly by incoming solar radiation. Not much warming or solar radiation penetrates deeper than about 30 centimeters, so SWARM calculates warming for 10 centimeters below the snow surface. If you've accidentally cut the roof of a snow cave thinner than about 30 centimeters, you've seen the sunlight coming through the thin spot. Various factors affect the shortwave radiation reaching the snow surface. The strong terrain factors are aspect and slope angle. For its calculations of the effective aspect and slope angle, SWARM uses idealized terrain, essentially an upside-down mixing bowl. Elevation effects are mostly due to shading by terrain features and trees. SWARM ignores these, so its calculations are independent of elevation. The other strong factors are the day of the year, the cloud cover, and the condition of the snow surface. Since an old snow surface absorbs more solar radiation than a fresh snow surface, SWARM calculates the absorbed solar radiation from the age of the snow surface.
So here is the SWARM spreadsheet. Let's start with the inputs in this box. Set the latitude and longitude for your forecast area. The units are in decimal degrees, the same as the default for Google Earth. These values are for Rogers Pass. Let's set the date to 2010, December the 11th. Suppose we're expecting overcast sky, and it snowed last night, so it is 0 days since the last snowfall. I'll skip the output graph on the right and focus on the one on the left, which shows the warming around the aspects of the compass. The innermost line is for 2.5 degrees of warming. The next line out is for 5 degrees of warming, and so on. We can select the slope angles to display. I'll select 40 degrees, which is approximately the slope angle of many start zones. We see about 1 degree of warming. It's the same on all aspects since we selected overcast sky. This is also displayed here in the yellow box for a 40 degree north aspect and a 40 degree south aspect. Now let's switch to a few clouds. The graph shows less than 1 degree of warming on steep north and 6 degrees of warming on steep south. Suppose it has not snowed for 5 days. The albedo will be lower and the snow will absorb more solar radiation. Still only 1 degree of warming on steep north, but now the graph shows 10 degrees of warming on steep south. You have probably noticed that the estimated warming on east and west aspects is the same. Now suppose the date is March the 11th. The graph shows about 2.5 degrees of warming on steep north and 15.5 degrees on steep south. But you say, what does 15.5 degrees of warming mean if the snow down 10 centimeters was at -5 degrees in the early morning? Well, in this case, the snow will start to melt after it warms up 5 degrees. Well, SWARM does not know the snow temperature prior to warming, but the estimated warming is proportional to the absorbed solar radiation. So the estimated warming can be considered an index of absorbed solar radiation even when the snow is not dry. Okay, the graph is visual, but how can we summarize the output for a hazard evaluation form or a field book? Just below the inputs, the yellow box displays SWARM 2.6/15.5 dry if Q. 2.6 is the estimated warming on a 40 degree north aspect. 15.5 degrees is the estimated warming on a 40 degree south aspect. These estimates assume the snow remains dry and the sky has few clouds.
There are some limitations to SWARM. Some arise from the limited data set used to develop the model, and some arise from the parameterizations used to keep the inputs simple. SWARM uses a daily average cloud cover, so variations in the cloud cover during the day are not taken into account. SWARM does not consider the effect of trees or nearby terrain. These may shade the snow surface from incoming solar radiation and or contribute to incoming long-wave radiation. If there is substantial variation in the near-surface snowpack properties, such as the presence of a melt-freeze crust on the south aspect and fresh dry snow on the shady north aspect, then SWARM's estimate of daytime warming will be less accurate. The data set used to calibrate SWARM did not include weather conditions such as strong wind or precipitation, either of which can affect the snow surface energy balance. SWARM was calibrated for a deep snowpack and will be less accurate where the snow is less than about 30 centimeters deep. As I mentioned, SWARM cannot predict melting. If the snow down 10 centimeters is at -5 degrees Celsius and SWARM estimates 10 degrees of daytime warming, well, the snow down 10 centimeters is only going to warm to 0 degrees and then start to melt. So, strictly speaking, the daytime warming is only accurate for dry snow. However, because the estimated warming is proportional to the absorbed solar radiation, SWARM's output, degrees of warming, is an index of absorbed solar radiation. What about the accuracy? Well, with the data available for verification, the accuracy is about 1.6 degrees Celsius. Recalling the experienced participants on the Advanced Avalanche course who estimated the solar radiation to be between negligible and intense, perhaps SWARM's visual output can help us understand how factors such as aspect, steepness, latitude, day of the year, cloud cover, and age of the snow surface affect snowpack warming due to solar radiation. SWARM does not replace our experience with daytime snowpack warming, but perhaps it can help us improve our estimation of snowpack warming over terrain, because sometimes, and only sometimes, snowpack warming increases the likelihood of avalanches and is one of the factors to be considered. We are grateful to these organizations that share the cost of ASARC's applied avalanche research. Many of these organizations were supporters at the time Laura Bakermans developed SWARM. Thank you.